Welcome to another video about the discrete time Fourier transform. So now let's go on with yet another example. So what's the discrete time Fourier transform of well, we're not on the pitch, we're not talking about football, so 1 over 3, but there is the same excitement. 1 over 3 to the n, u of n minus 3. Okay, so once again, let's start from the very same definition. So what does the definition tell us? Well, capital F of x of e to the j omega is equal to the sum of of n that goes from negative infinity to positive infinity of x to x of n e to the negative j omega n. But in this case, we don't have the unit step. We have the unit step of n minus 3. What does it mean? Well, it means that it's shifted on the right by 3. In other words, it's still jumping at 1, but it's not going to jump at 1 at 0. Instead, it's going to jump at 1 at 3. And it's just easy to plot. Like, it's essentially the very same thing we have been seeing all over again. So we have 0 here. We're jumping to 1, but not a 0. So if we go to 1, 2, 3, 4, 5, 6, all the way to infinity, we are jumping at 1. We're jumping to 1 at 3. So we're essentially staying at 0 till we get to 3, and then we're jumping. We're jumping, when we get to 3, we're jumping and staying at 1. So what does it mean for us is that just like when we wrote this sum and replaced the u of n with n that goes from 0 all the way to infinity, from here, since we're jumping at 1 at 3, we're going to have from n that goes from 3 to positive infinity, because we're jumping here, not here, here. So we have x of e to the j omega equal to the sum of n that goes from 3 to positive infinity of, well, this 1 over 3 to the n e to the negative j omega n. What do we do from here? Well, we have n here, we have n here. How about we put them together? So x of e to the j omega is equal to the very same sum of n that goes from 3 to positive infinity of 1 over 3 e to the negative j omega, all raised to the n. Okay, so we're almost where we want, because once again, what we want is to get to the very common form of the sum from n that goes from 0 to positive infinity of a to the n, because we know that this solution is 1 over 1 minus a. So how do we get here from here? Well, we have something raised to the n, which is good. We go to positive infinity, which is good, but we're not starting from 0, we're starting from 3 because we are shifted. So what do we do? Well, we can actually say, let's put n minus 3 equal to m, which means that n is actually m plus 3. So what do we get? Well, we get x of e to the j omega equal to the sum from m that goes from 0 to positive infinity of 1 over 3 e to the negative j omega m plus 3. So we don't have n anymore, and we don't have n anymore. And of course, by the way, over here it's the same. I mean, we're essentially subtracting, like, it doesn't matter if we add or subtract 3 to positive infinity. Is not going to make any difference. So we're still gonna have positive infinity. Doesn't matter. Positive infinity is a big, bold guy, and doesn't matter if you throw something as small as 3 at him. Anyway, jokes aside, let's crack on. Let's go on. And where do we go from here? Well, where do we go from here is saying, okay, we have m. This part is fine because we have from m that goes from 0 to positive infinity, so it's fine. Which is this. Here we have a to the n. Here we have m something to the m plus 3. I don't want that plus 3, but we're lucky because once again we can use the property of powers, and we can basically split this in two. So we can say, okay, this is capital X of e to the j omega equal to the sum of m that goes from 0 to positive infinity of 1 over 3 e to the negative j omega to the all raised to the power of m, which is what we want, times 1 over 3 e to the negative j omega raised to the power of 3. So we basically split those. But hold on a second, this one has nothing to do with m, so we can basically bring this on this side, so outside of the sum. So I can say, okay, this has nothing to do with this, so we got x of e to the j omega equal to 1 over 3 e to the negative j omega raised to the power of 3, of course, times the sum of m that goes from 0 to positive infinity of 1 over 3 e to the negative j omega, all raised to the power of m. So we are basically almost done, because, well, first of all, this one, let's get on with this one. Well, this is just a power, like, we have 3 to the power of 3, which is 27, so 1 over 27 e to the negative 3 j omega times, well, this is exactly what we wanted. We can say, well, let's just do it once again. Let's put 1 over 3 e to the negative j omega equal to p. So once we have done that, we have the sum of m that goes from 0 to positive infinity of, well, p to the m. Now that we have p to the m, we know what this is going to be. So x of e to the j omega, right now I'm just multiplying, bringing this e here. So e to the negative 3j omega over 27 times, well, what do we have here? We have 1 over, we are basically applying the formula 1 over 1 minus 8, so 1 over 1 minus p. And we're almost done, because now that we have this, we can say x of e to the j omega is equal to, well, we're just multiplying those. So we get e to the negative 3j omega over 27 times 1 minus p. But one minus, but p was actually 1 over 3 e to the negative j omega. So our final result is going to be x of e to the j omega equal to this. We're going to leave alone the numerator. So e to the negative 3 j omega over 27 times 1 minus 1 over 3 e to the negative j omega. And this is our final solution. So our discrete time Fourier transform of x of n equal 1 over 3 to the n u of n minus 3.